a course material on CE 3351 Surveying and Leveling, presented by R. Rajiv Gandhi, Assistant Professor, Department of Agriculture Engineering, Rohini College of Engineering and Technology, Palkulam. GPS error sources. If the world was like a laboratory with perfect laboratory condition basic, GPS would be a lot more accurate. Unfortunately, it is not so and had plenty of opportunities for a radio-based system that span the entire planet to get fouled up. Inaccuracies in GPS signal come to from the variety of sources like satellite clocks, imperfect orbits, and especially from the signal stripped through the Earth atmosphere. Since these inaccuracies are variable, it is hard to predict what they will be in order to correct for them. Although these errors are small, but to get the kind of accessories, some critical positioning jobs require all the errors, no matter how minor, are to be minimized. What is needed in a way to measure the actual errors as then happen. The error sources can be classified into three groups, namely satellite related errors, propagation medium related errors, and receiver related errors. These are known as systematic errors. However, sometimes errors are introduced internationally known as selective availability. Systematic error, satellite error. GPS satellites are equipped with very accurate atomic clocks, but as good as these clocks are, they are not perfect. Slight inaccuracies in their timekeeping ultimately lead to inaccuracies in our position measurement. The satellite position in space is also important equally because it is the starting point for all the GPS calculations. GPS satellites are placed into very high orbit and so are relatively free from the perturbing effects of the Earth's upper atmosphere, but even so, they still drift slightly from their predicted orbit, contributing to the errors. Signal propagation errors. GPS satellite transmit their timing information by ratio, and that is another source of error because radio signals in the Earth atmosphere do not behave as predictably desired. It is assumed that radio signals traverse at the speed of light, which is presumably a constant. However, the speed of light is not constant. It is only constant in vacuum. In the real world, light slows down depending on what is the traversing through. As a GPS signal come down through the charged particles in the ionosphere and then through the water vapor in the troposphere, it gets delayed a little since calculation of distance assume a constant speed of light. This delay result into a miscalculation of the satellite distance, which is translate into the error in position. Good receivers add in a correction factors for a typical trip through the Earth atmosphere, which helps, but since the atmosphere varies from point to point and moment to moment, no correction factor or atmospheric model can accurately compensate for the delay that actually occur. Receiver error. The receiver are also not perfect. They can induce their own errors, which usually stem from their clock or internal noise, multipath, and antenna phase center variations. Multipath, as a GPS signals arrives at the surface of the Earth, it may get reflected by local obstructions and gets the receiver's antenna via more than one path. This form of error is called multipath error because in sense the signal is getting to the antenna by multiple paths. First, the antenna receives the direct signals, it being the fastest, and then the reflected signals arrive at a little later. These delayed signals can interface with the direct signal, giving noisy results, secondary effect, and reflection at the satellite during signal transmission. The influence of the multipath, however, can be estimated by using a combination of L1 and L2 codes and carries space measurement. The principle is based on the fact that troposphere clock errors and relativistic effect influence code and the carrier phase by the same amount. This is not true for ionospheric refraction and the multipath which are frequently dependent, taking ionospheric free code range and carry space and forming corresponding differences all for maintained effects expected for multipath cancel out. The most effective countermeasures the multipath is to be avoided where it could be a problem. The eliminates of multipath signals is also possible by selecting an antenna that takes advantages of the single polarization. GPS signals are right-handed circulately polarized whereas the reflected signals are left-handed polarized. Antenna phase center offset and variations. The phase center of the antenna is the point to which the radio signal measurement is referred that generally is not identical with the geometric antenna center. The offset depends on the elevation, the azimuth and the intensity of the satellite signal, and it's different for L1 and L2 codes. Also, the true antenna phase center may be different from the manufacturer indicator center. This antenna offset may simply arise from inaccurate production series. Thank you.